Chapter 13 is where we're going next. Chapter 13, 14, 15, energy, heat, light, and electromagnetic waves. Chapter 16, sound. So kind of physics type stuff, delve into chemistry just a little bit. And energy, for our purposes, is the ability to do work. What is work? Pretty much it's going to involve movement of anything. So if I put a drop of food coloring into water and that food coloring moves, well, then there was some sort of energy involved. Okay, it's going to, I didn't have to shake it, I didn't have to do anything. There was energy in the water. There was movement of the water molecules already, so there was energy in there. If I'm moving my hands, obviously that's energy. If I'm lifting a weight, that's using energy. I'm doing work. Life is largely about energy conversions. And by that, I mean the primary source of energy for this planet is the sun. Okay, we have this star that's shining through space, and we get energy in the form of light and heat, and it's coming to the planet all the time. Plants are able to capture a small portion of that energy and convert the light energy into chemical energy. They're taking the energy of light, they are taking apart water molecules, they're combining carbon dioxide and water, and they are making sugars. They're making glucose molecules. As a byproduct, they're releasing oxygen. But with these glucose molecules, they have then captured in a sugar molecule the energy of sunlight. The energy of sunlight. And using excess energy that they've captured, they're able to stick multiple glucose molecules together, make big chains of them, shape them into new things. The cells of the plant are not running directly on glucose. We'll talk more about that in another chapter. All the cells on this planet are running on ATP. It's a high energy molecule. But to get the ATP, they're breaking apart glucose molecules. To build any carbohydrates, they're putting together sugar molecules. So, needless to say, energy coming in all the time, a small portion of the energy captured through photosynthesis, and so the energy has been transformed from light energy into chemical energy. Now, the energy hasn't been added to. We can't make new energy. We can't create it or destroy it, but we can transform it. We can change it to something different. And so a portion of it was transformed and is now in chemical energy. Now, I can come along and eat some of that plant. I can eat the leaves, I can eat the seeds, I can eat the fruits. I can eat whatever I want, and some of it I will be able to extract that chemical energy and convert it from one form of chemical energy to another form in my cells. So the carbohydrates of the plant, I can break them apart, use them to drive my cellular functions, use them to build new things inside my body. So, hey, I'm solar powered. You know, it's just one step from me to the sun. I just have to eat plants. I can have it as two steps. I can eat a cow that was eating plants that was getting energy from the sun. Okay, but it's still energy conversions. Every time I wiggle my hands, use my voice, think a thought, any of that, it's using chemical energy that I acquired through eating. And it was acquired by the plants through photosynthesizing, just capturing that sunlight. And we'll talk more about photosynthesis someday. Okay, so we have all that good stuff going on for how we're actually getting energy. Now there's more than just sunlight in terms of the energy of the planet. There's heat. This planet hasn't finished cooling off. You know, it was very, very hot, and the inside of it is still very hot. There's nuclear energy, and we can control that to an extent. And that's a totally, that's not solar energy at all. Gravitational potential energy. That would be like using a dam and the the energy of the water backed up behind the dam that's creating a force on the turbines down at the bottom of the dam. So we can spin the turbine. So we can go from the gravitational potential energy of the water to spinning a turbine, again transforming the energy from one form to another, and then that kinetic energy of the spinning turbine can be converted into electrical energy. So again, conversion from one energy source to another. So if there's any sort of motion involved, that's a type of kinetic energy. Okay, any sort of, my hand has kinetic energy. While it's sitting here, there's potential energy. During that drop, there was kinetic energy. Okay, and as soon as it stops moving, that's the end of the kinetic energy. Now, when it hits, there's going to be a small release of energy into the surrounding environment in the form of heat. Any transfer of energy, there's always going to be a little loss in the form of heat. You lose energy in many forms. Well, you lose energy every time you transform, and heat is very disorganized sort of energy. So if I eat a hamburger and I convert that chemical energy into chemical energy of my cells, just the fact that I'm having to do those conversions, I actually lose most of the energy as heat, which is fine because I'm a mammal, and so I'm putting that heat to use. But even a bacteria eating sugars or eating dead cat or whatever it's eating, it's producing heat. It's losing most of the energy of that dead animal or the dead grass or whatever it's eating. Most of the energy is being lost as heat. So every time you transform, you lose most of the energy. You can't, there's nothing that's 100% efficient at transforming. Another way to think of this is when you drop a bouncy ball, if I drop it from this high, well, okay, from here to here, it doesn't go bounce up higher, and it doesn't bounce up as high as it was, right? It will bounce and it will be lower and lower and lower and lower. It's losing energy each time, even though all it's doing is bouncing. So most of the energy, most of the gasoline that you put in your car, most of that energy is lost as heat. You have to have a whole cooling system on your car just to deal with that. Most of the energy from the food that you eat, most of it is lost as heat. It's not used for movement or thoughts or cellular chemical reactions. Most of it's just lost. Anyway, kinetic energy, if it's moving, there's kinetic energy. And if it's not moving, then the energy is stored inside of it. So there's potential energy. And potential energy is just any form of stored energy. So it can be a spring that's ready to go boing. It can be, the fact that this is up, there's potential energy because it can release kinetic, it can move, right? There's a potential there. Water behind a dam is potential kinetic energy. A bullet with the gunpowder sitting in it, that's potential energy. There's potential energy in places we don't think of there being potential energy because we don't get energy out of it usually. A brick. Well, it's just a brick. It's not doing anything. It's not moving. There's still some potential energy in it. Either the brick is up high and it could fall, so there's the gravitational potential energy in it, or if you could somehow, decompose it chemically, you could release some chemical energy from it. So even though the energy isn't necessarily available, most things have quite a bit of potential energy. There's the potential energy of the atoms themselves, and if you could take apart the atoms in a nuclear reaction, well, that would release tremendous amounts of energy, right? We do this sometimes with nuclear bombs or nuclear energy plants. Okay. Gravity. Gravity is a strange thing. Objects attract other objects. So this pen and this water bottle, they're attracted to each other. The gravity is actually a very weak form of attraction. The fact that things fall to the ground is because the Earth is massive. So even though this is small or this is small, there's force. You know, the Earth is big, and so the attraction when the Earth is being attracted to the pen, and the pen is being attracted to the Earth. Just the Earth is so much more massive. It's not going to be jumping up to the pen. The pen is going to fall down to the Earth. The closer things get together, the greater the gravitational attraction. This is why for a spacecraft, it takes tons of energy to get up. And once you're out of this atmosphere, you get to a point where you're not going to fall back down. You know, you can get in orbit around the planet and not fall back in, because you're far enough away from the planet that the gravitational energy is less. There's still gravitational energy there, or gravitational attraction, which is why you're in orbit around the Earth instead of just floating off into space. The gravity between the Earth and the moon is keeping the moon in orbit. So anyway, if the moon came closer, your gravity would be stronger and stronger and stronger. You could, you know, the Earth and the moon could collide. What else do we want to say about that? Gravity's at play whenever things are going to fall. Okay, so there you go. Water, ball, rock, whatever is falling down. And as it's falling, it's going to get faster and faster and faster to a point. There's going to be friction that prevents it from speeding up indefinitely. But if you jump out of an airplane, the first second, you're going to cover 32 feet. But it's 32 feet per second per second. And so you're going to be accelerating. Just a second. I don't think this is right. This is going 32 feet per second, but this is not showing acceleration. 160 feet in 5 seconds is the same as 32 feet in 1 second. That's moving the same speed. That's not accelerating. So this slide is incorrect. You should be adding to your speed. So the first second, yeah, you went 32 feet. During the second second, you went 64 feet during that second. Okay, during that second. So you went 64 plus 32 total. Now after 2 seconds, you're 96 feet down, not 64. So in the 5th second, you went 160 feet. Not after 5 seconds. You know, it's not that you've covered 160 feet in 5 seconds. In 1 second, you went 160 feet down in that 5th second. So you're going faster and faster and faster. You will reach a maximum, you know, a terminal velocity because the air resistance. In a vacuum, there you don't have to deal with the air resistance, and so whether you drop a feather or a hammer, they're going to go at the same speed. Well, it's going to be a little slower if you're out on the moon in a vacuum. And in fact, they did this experiment on the moon, and you can find a video, I should look for that, where they drop a hammer and a feather at the same time, and they go at the same time. Now, why do they not drop at the same speed on our planet here? Because we have an atmosphere, because we're not in a vacuum, and the feather is spread out. It has a big surface area. It catches the wind, and so given its weight, is very light, and it has a big surface area for the amount of mass that it has, it drops slower. But if you take that same feather and you crumple it up into a small thing, like a penny-sized thing, and it will follow the same speed as a hammer. Okay. Internal energy. If you look at an atom, which you cannot do, not even with a really good microscope, you cannot look at atoms, I'm sorry to say. but you can look at the effect of atoms vibrating. Atoms they have internal energy, and they are always moving as long as there's any amount of heat, and it can be minus 200 degrees. That's still some amount of heat. Until you get to absolute 0 degrees Kelvin, there's going to be molecular motion, atomic energy moving in these atoms. They'll shake, the electrons will spin, the atoms are going to be moving around. And you know this just because, you know, I spray perfume, it doesn't stay right here in this cloud that I sprayed it. It moves throughout the room. Somebody on the other side of the room is going to be smelling it. And that means that there was movement. The little molecules of perfume went boing, 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 boing. They're bouncing off all the air molecules. Boing, 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 boing. It went right up the guy's nose and activated the chemical receptor. If there wasn't motion, it would have just stayed there. Or I guess with gravity, it would have just gone to the ground there. Okay, conservation of energy. The amount of energy for the whole entire universe is constant. You can transform it from one form to another, but you can't make new, you can't destroy it, you cannot create it or destroy it. You can only change it from one form to the next. That's really weird to think about. And it's kind of mind-blowing to think that the entire energy of the universe was contained in some pinpoint amount, boom, before it exploded instantly into this giant universe. That gets really weird to think about that kind of physics. And it's really weird to think that the universe, you know, continues to expand, and that the amount of energy is the same. And we're transforming it. Anyway, I'm going to not get too much into astrophysics. Let's move along. We can't create it. We cannot destroy it. Einstein's famous equation, E equals mc squared, talks about transformation of energy from one form to the next, specifically if you're taking energy by taking apart an atom or transforming an atom. And so this is a release of energy. E, big E for energy, equals the mass. So you can actually convert mass of something directly to energy. You can convert mass to energy. Mass, therefore, is a form of energy. Just the fact that this, you know, that something has mass, that it takes up space. And anyway, we don't do this much, right? The world around us, mass is not getting converted to energy. That's not the type of energy transformation we see in the world around us. This is energy transformation of nuclear reactions. Your sun, the star in our system, and all other stars are running off of nuclear fission. They are doing nuclear reactions. The energy that's coming from them is following E equals mc squared. So E is energy, M is mass, C is a constant, and the constant, is the speed of light. The speed of light is huge, huge, huge. So how big, when I say speed of light is huge, let me just bring that up for you, because I can never remember the exact. 299,792,458 meters per second, or approximately 3 times 10 to the 8th meters per second. If you want to know in miles per hour, that's approximately 186,000 miles per second, or 671 million miles per hour. 671 million miles per hour, or 186,000 miles per second. That's a really big number. If you take that really big number and you square it, 186,000 miles per second squared, then it doesn't matter that the mass, if the mass could be teensy tiny, if you're converting a teensy tiny bit of mass to energy, you'll get a lot of energy because you're multiplying it by a huge number squared. So that's why nuclear reactions release so much energy, is this huge number here. If you were able to take a cup of water and run it through a fusion reaction, and by the way, I misspoke. I said stars are running on fission. That's not true. Stars are running on fusion, and there is a difference. So fusion. If you ran water through a fusion reaction, a cup of water, you'd have enough energy to drive your car all year long for a full year. 10,000 miles easily on a cup of water. That's how much energy is in the atoms. And we would very much like to have controlled fusion reactions on this planet. We have not been able to do that. We can do fission, which is ripping apart molecules. That's great. It releases the same, E equals mc squared, but you're left with radioactive byproducts, and they're very dangerous. If we could do fusion, we wouldn't have that problem. Okay, we're not completely done here, but I'm going to stop here because I really have no clue if this is working.